Today what I'd like to do is look at an alternate way of locating objects in two-dimensional space called polar coordinates. This is what we're used to. This is Cartesian coordinates, the old way. We would mark a location in 2D by how much left-right, how much up-down, and that gives us our XY pair. In polar coordinates, instead of sticking to a grid, if you like, we go as the crow flies. So if you start at the origin, that point is some distance r. We usually use r for radii, because that's radiating out from the origin. And then that radii will make some angle here, theta, with the positive x-axis. And you can identify any spot in two-dimensional space by how far it is from the origin and what that angle is with the x-axis. So in polar coordinates, this is going to have an ordered pair r theta. So we'll be looking at some curves in polar coordinates. We'll look at the coordinate system itself, how to move back and forth between the two systems. Some curves naturally lend themselves to polar coordinates. Things that tend to go around the origin, as we'll see later, tend to represent well in polar coordinates. So the first thing I'd like to do with this new coordinate system is just get us used to the values of r and theta and how they relate to x and y. So if we draw on here, at least in the first quadrant, to make life easy, where everything is positive, we have a right triangle, right, where this side is x and this side is y. So when we combine x, y, r, and theta, we have this nice right triangle where we have all the sides and we have the angles. So we should be able to relate everything to each other by right triangle trig. So first of all, let's express our old x and y in terms of this new r and theta. So first of all, whoops, let me fix that. Talking and writing at the same time. This is x, this is y. All right, so if we wanted to relate x to r and theta, those three relate by the cosine function, right? Because cosine's adjacent over hypotenuse. So cosine of theta is x over r, which solving that for x means x is r cosine theta. Likewise, we can relate y to r and theta via sine. So sine theta is y over r, so y is r sine theta. So there's two of our conversion equations. Given any xy point, given any r theta pair, you can get an xy. What about the other direction? So what if we started with x and y and wanted to get r and theta? So first of all, relating x and y to r, we see we've got a right triangle. Pythagoras is the natural way to relate those. So we've got, let me box these in for us. So there's our conversion going one way. The other way, x squared plus y squared is r squared. Now you could take the square root if you'd like, but you will put a plus minus on there. One thing that's interesting about polar coordinates is we are going to allow r's to take on any value, positive or negative. And when we get to an example, I'll explain to you what we mean by a negative radius. So let's just leave that in terms of Pythagoras and not solve r by taking plus minus square root. And then relating x and y to theta, well, the x and y relate to theta via the tangent function. Tangent theta is opposite over adjacent, so y over x. So there's our four conversions. Now, going one way, given an r and theta, there is only one x and y. One thing about the Cartesian system is there is only one ordered pair that represents that dot. In polar, which is both a blessing and a curse, is that point has infinitely many r theta pairs. Because I just mentioned we're going to allow r to be both plus or minus. That point will have both a positive and a negative r, and I'll explain later how that works. But also, we know from trigonometry that we can just keep going around and around. So that angle, you could add 2 pi, add another 2 pi, or subtract 2 pi, subtract 2 pi. So there's infinitely many theta and 2 r's that would go with that. So that frees us up to do some interesting things graphically, but it also makes us, we have to be a little bit careful with some of the algebra we do in polar coordinates. Now, I said that I didn't want to solve this for r because it leads to a plus or minus, so we'll just leave it like this. Also, I don't want to solve this for theta. I don't want to say theta is tan inverse of y over x, because remember, tan inverse would only ever give you an angle in these two quadrants, quadrant 1 and quadrant 4. If you're over here, tan inverse will not give you theta. You'll have to do an adjustment. And I'll remind you of how we do that from trig when we do an example here in just one sec. OK, so let's look at converting an xy pair over to polar, which is the more interesting thing because it's going to have infinitely many representations. So let's start off with a point in polar coordinates, or excuse me, in Cartesian coordinates, and then we'll go to polar. So this point right here in Cartesian is -3, -4. And I intentionally made it not in the first and fourth quadrants, so we definitely are going to have to use our knowledge of the quadrants when it comes time to convert to theta. OK, so first of all, r. Let's stick with positive r's for just a second because it's more intuitive. So we want r, the distance from the origin to there. And like I said, we'll take the positive measure. So really just the positive square root there. So r is square root of -3 squared plus -4 squared. And this is our famous Pythagorean triple 3, 4, 5 triangle. So one representation is with a positive 5. Now what about the angle? Now when we go to find theta, if you just take theta to be tan inverse of y over x, so tan inverse of -4 over -3. Well, think about this. -4 over -3, that's a positive number. It's a positive 4/3. Tangent's positive here and here, but this quadrant is where inverse tangent's going to give us. So really, if you put that in your calculator, that is tan inverse of -4 over -3. And that's not the angle we want. We want the angle all the way around to there. That's the theta. So remember, the adjustment from trig is to add pi. It works even if you're down here. If your point was up here, tan inverse will be down here. Adding pi gets you. You're always out the other side of the origin. So the adjustment is always to add pi if you're in these two quadrants. So there's our r and our theta. There's one possibility. So we could label this point as 5, tan inverse, and just reducing that down, 4/3 plus pi. Now, I intentionally did not finish off those parentheses. We know that you could keep measuring angles by going around and around and around and around, right? So you could keep going in the positive direction, add another 2 pi to this, and you'll be back here, right? Add another 2 pi, you'll be back here. Add another 2 pi, or subtract 2 pi, subtract 2 pi. So to fully describe it with a positive r, I really have to say plus 2 pi k, where that k is any integer. So a positive integer or positive whole number or negative whole number. So going either the positive or negative direction. Now, the less intuitive way is we do allow for negative r's. And so what we mean by a negative r is I think of polar coordinates as if I was standing at the origin, and to get to a certain point I'd have to rotate myself around to whatever angle I am, and then r tells me how far to walk towards that point. So negative r means to walk backwards. So to get to a point in 2D space, if you're going to walk backwards, you have to face away from it and then walk backwards to it. So to get to this point, I would want to face that way, but walk backwards. So with a negative 5, the angle would actually be just the tan inverse, right? Because that's the way we would want to face, but we would want to walk backwards. So here there's no adjustment needed. It's just tan inverse of 4/3. That's going to give us that angle in the first quadrant, and then we're going to walk backwards. And again, you want to face that way, but you could go round and round, adding 2 pi or subtracting 2 pi. So we do have to represent all possible combinations. We need to put that plus 2 pi k on there. So that is all the representations in polar, either facing the point with a positive r or facing away with a negative r. And then every possible angle by including all your times that you can rotate around. And so, like I said at the beginning, there's some advantages to this fact that there's not a unique representation, but there's also some disadvantages when it comes to some computation. For example, finding the point of intersection of two curves in polar, they may cross at a point that has a different name. So they're not equal even though they're intersecting. So we'll see some of that later on. Now to go the other direction is a lot easier. If you're given an r and a theta, then you can just compute x and y. There's no adjustments. There's only one answer because there's not infinitely many xy pairs that go to one point. So the other direction is much easier. But in your homework, they may tell you to just give the representation with a positive r and a theta between 0 and 2 pi, or a negative r and some range of angles. Then there will only be one label because they've reduced the domain of thetas there. So this is the system we'll be looking at. We'll do curves in polar, and then we'll move on and do some calculus, slopes, areas, and lengths. So we'll be looking in this coordinate system for the next couple of sections.